Hello again, and welcome to part 3. I'm going to remind you again that it's useful to read the companion notes that pretty much have these slides repeated on them from course collateral, and also read your book. They have different examples than the ones I'm doing, and so that can reinforce your understandings as well. We're continuing to make this more and more realistic. Last time we introduced having dampening. And now what we're going to do is talk about a differential equation where we have a forced motion or a driven or forced motion. That means we're adding an f of t that is representing a driving force. So adding that then to our system of it's not a system, to the differential equation we have, we get a plus lowercase f of t here, and when we divide by the m it becomes a different. In this case, I'll call it capital F of t. But now what we have is a non-homogeneous equation, and we have to use some of our techniques that we've studied before to solve them. Now, when the driving force is a periodic function, such as those shown there, the general solution is the sum of a non-periodic function, the complementary solution, and a periodic function, which will represent the particular solution. And the complementary solution can die off as time increases, that is, if its limits equal to 0. So for large values, the displacement are closely approximated by the particular solution. And the complementary solution is said to be a transient term or transient solution. I think we've talked about that before. And the particular solution is what's called a steady state or ongoing solution. And so that's what we're doing. We're going to start by talking about driving motion without dampening. Now, with a periodic impressed force and no damping force, there is no transient term in the solution of a problem. So what we'll see is that whenever we have this impressed force with a frequency that is either near or nearly the same as the frequency of the free undamped vibrations, this can cause some severe problems in an oscillatory mechanical system. Here, for example, you could say, oh, it's bouncing back and forth ever more violently, and eventually it will exceed the elastic limit of the spring and cause severe damage. You might say, well, I didn't really care about the spring, but no, you care about an airplane wing, which is modeled in the same way. And so you don't want things exceeding its elastic limit. As an engineer, you're very concerned about that. Now, one might argue that the resonating model is completely unrealistic because it ignores the retarding effects of an ever-present dampening force. And this is true for pure resonance, cannot occur whenever there's even a little bit of dampening taken into consideration. Large and equally destructive amplitudes of a vibration are possible if there's a big difference between, if it is close to that. And there's some examples that happen with that. And in fact, we're going to look at an example right now that shows what can happen. So we have and this time we're doing metric system. A 3 kilogram object is attached to a spring, and it stretches the spring, it looks like 392 millimeters, so you have to be mindful of the units on this, by itself. There is no dampening in the system, but the forcing function is of that form. Capital F of t, this is after you've already divided by m, is a 10 cosine omega t, and that's attached to the object, and the system will experience resonance. Now they're talking about pure resonance here, so the omega t here has to be the natural frequency of the system that we had to start with. If the object is initially displaced 20 centimeters now, we got millimeters, centimeters, and meters all in the same problem, from its equilibrium position, and given a velocity of 10 centimeters per second upward, find the displacement at any time t. So that's what we're going to be solving in this problem, and we'll see what happens when there is pure resonance happening. So as before, the spring constant is found by the mg, the weight, divided by the length that the spring is extended. But this time, we're not using 32, it's not pounds, so that is kilograms, and that's the 9.8 number, and there I changed that into meters, and so we get a number of 75 for K. So that means that if we talk about the original system, and I put a omega sub 0 here to represent the original system, but that's the spring constant, which we found to be 75 divided by 3, and when you do the square root of all that, you will get, let's see, yeah, 3 goes into 75 25 times, and the square root of 25 is 5, so that's good. So then when we substitute back into our original equation, what we find is that this is 3. Actually, I guess I should not have said that I divided through by the mass on this, because this really is the thing in my previous notation that's the lowercase f, but still that's an impressed function. But now we divide all the way through by 3, and we end up with an equation that we have to solve, and that's going to end up being d squared plus 25, and then we get 10 over 3 here, and so on and so forth. Well, and we have initial conditions, and again, these are in metric systems and obeying the sign conventions that we had previously. Now we know how to solve that, and so what will happen is this part here is a solution to the homogeneous, and it's the complementary solution, I guess we call it. And then here is the particular solution that we get for this to get this term t. So that's the particular solution. When we apply the initial conditions, what we will get is this as our solution. And notice that we have these are linear combinations of sines and cosines, which are fine. But then here what we have is a 1/3 t times sine of 5t. So you see that t being there makes it really big, because this is going to oscillate, but as t gets bigger, these oscillations get bigger and bigger as well. To graph this, I went ahead and changed this into an expression with a cosine, and so I changed the particular, not the particular, I changed the complementary part of that into that. Doing that, here I found what phi1 was. Now look here, now I have a negative and a positive, so that puts us actually in the fourth quadrant, and you might remember that this was always cosine, and this was omega t, but then we would minus phi, so that is a minus angle. It's in the fourth quadrant, so that's why we get a plus there, and it's plus 1/3 t sine of 5t. So again, this is going to be just something that oscillates a bit and things like that as t goes on. But this thing becomes dominant, and in fact what happens over time is you get this, and this violent kind of oscillation will destroy the engineering system that you put together. So one must be careful about being at or near the frequency of the spring system or the simple harmonic system that we're studying. One final example, and this one puts everything together. Before we didn't have any dampening, now we have dampening. It says take the system from the last example. I guess this is the system from the very last example that we talked about, but now we're going to add dampening, and that means that you won't have pure resonance, and hopefully we put in enough damping that it will behave differently. Let's see, so we add in a damper that will exert a force of 45 newtons when the velocity is 50 centimeters per second. Now this means we're assuming that the force, the damping force, is proportional to the velocity. Again, that's not what is going to happen on your take-home problem, so read it carefully. It's a different kind of problem to solve. But we will take this and work through a solution. So first thing we're going to do is find the coefficient of the dampening, and using the information we find that beta is 90, so that's a nice big dampening factor. And the beta, the 90, will find itself here being multiplied by the u prime, and if we put all that information together, we end up with this. We're going to divide all the way through by 3. These are the initial conditions that we had on the last problem, and this time what will happen is we will get a solutions of, and the roots of that are going to be minus 15 plus 10 root 2 and minus 15 minus 10 root 2. And that's going to be my complementary solution with those constants. And then my particular solution this time is going to be 1 over 45 because again the b has changed. So it's going to be 1 over 45 sine of 5t. And so you see you don't have the t factor in here this time because of the other nature of the solution. So our final solution when we plug in the initial conditions and use engineering calculator is we get u of t is equal to that plus this. And you can see as t goes to infinity, these things die out, so it starts looking more and more like 1 over 45 sine of 5t as time goes on. And here's the picture, and you see it does, and these die out, and you end up having something that is kind of nice going forward. So we've really talked about all of those kind of examples. I am going to make a couple of more remarks. One of those is an analogy. And I think in your book, in addition to many books, this really applies to many such things. And here we're talking about how this applies to electrical engineering, and these are called LRC circuits. That is impedance, resistance, and capacitance circuits. And here's kind of a picture how people would draw those. That's not a spring anymore. That's called an inductance coil. It has to do with current going through causing magnetism. There's an electromotive force that's on the outside, so that's the external driving function. R is a resistance over there, and there's a capacitance. And in your electrical engineering courses or circuit courses, you'll be studying those quite a bit. But you see, here's the kind of equation that we studied before, where we had the dampening force, the external force, as well as the undamped component of it. But if we talk about the current in a LRC circuit, and you look down here, you say, well, it looks pretty much the same. The role of M is being played by the inductance. The role of the dampening factor is associated with R, and the role of K is 1 over the capacitance, and we have our electromotive force on the other side. And if we put in the fact that the change in current with respect to time, it becomes not a first order equation, but it becomes a second order differential equation, which you can see it matches up identically. So if you understand how to solve the problems that we did, you'll understand how to solve this. And this is the kind of picture that's associated with your take-home assignment, and doing modeling on this and solving the differential equations, what I'm asking you to do. And we will have a different dampening factor associated with this, so there'll be some work involved with that. This concludes part 3, and in fact concludes this series of things. So please realize that time is precious. Each day must count. Do the math. It will make you strong. Take care, and I look forward to seeing you in class.